Hi everybody, we're in lesson 4 today, talking about multiple angle identities. We're going to look at different categories. There are double angle identities, that's one category. You notice cosine has 3 formulas that can be used. There are half angle identities when you want half of an angle. Sine and cosine look very similar. The only difference is the subtraction in the sine of a half angle and addition in the cosine of a half an angle. And then again, tangent has 3 different formulas that can be used interchangeably. And then we have power reducing formulas where you can take an angle that's being squared and cut it into a power of 1 using these 3 formulas. So let's jump right in. Our first example, we're going to prove the sine of a double angle using the sum and difference formulas from lesson 3. So I just want to say that the sine of u plus u would give me that 2u, where 2u can be broken up instead of multiplication as addition. And recall from the last lesson that when we expanded the sine of the sum of 2 angles, that pattern was sine, cosine, cosine, sine, and we alternated this first u and the second u. We also kept addition in the formula. So sine of the first angle, cosine of the second angle, plus cosine of the first angle times sine of the second angle. And using the fact that addition or that multiplication is commutative, I could rewrite cosine times sine as sine times cosine, and then we have 2 of the same terms, sine times cosine and sine times cosine, which adds up to 2 sine times cosine of our angle u. So we've proven that identity. Our second example, we want to prove that cosine to the 4th minus sine to the 4th is equal to cosine of a double angle. So we could show that by recalling that any number, say cosine squared, that quantity squared would give us cosine to the 4th by properties of exponents. And the same thing, sine squared of theta quantity squared would also give us sine to the 4th. So how can we show that that's the cosine of a double angle? Now, do you recognize that this term squared minus this term squared is the difference of 2 squares, which allows us to factor the cosine squared of theta plus the sine squared of theta, and then times the quantity cosine squared theta minus sine squared theta. So we factored the difference of 2 squares as the product of 2 binomials. So is that equivalent to cosine 2 theta? Now, do you recognize this is the Pythagorean identity, that sine squared plus cosine squared is 1. So this term is 1. And 1 times cosine squared theta minus sine squared theta is going to be equivalent to cosine 2 theta. Now, if you don't recognize this, go back and recall, let's just think for a minute, what the cosine of theta plus theta, which is cosine 2 theta, what did that look like from our last lesson? You know, the pattern for cosine of the sum of 2 angles was cosine, cosine, sine, sine. But when the sum of the 2 angles was expanded, we had difference there. And here you can recognize that you've got cosine squared theta minus sine squared theta, which is our term right here. So the cosine of 2 theta, is that thinking from lesson 3. So if we move that out of the way here, then you can recognize that the cosine squared of theta minus sine squared of theta is the cosine to theta, and we have proven that identity in this second example. I just wanted to make sure you understood that from lesson 3. So moving along, we're going to look at these double angles from a geometric point of view. And we want to use the formula for sine of 2 theta, which was 2 sine theta cosine theta. But we have this picture. And in order to resolve our problem, we need the sine of our angle theta. And sine is opposite over hypotenuse. So resolving that, a squared plus b squared equals hypotenuse squared. It looks like we have the square root of 17 for that hypotenuse. So the sine of that particular triangle would be opposite over hypotenuse, and the cosine would be adjacent over hypotenuse. And multiplying that out, it looks like we have 8 over 17. So the sine of the double angle would be 8/17. Now, like I said at the beginning, we've got 3 formulas for cosine of a double angle, and I'm just going to pick up with the cosine squared minus sine squared and use that particular formula based on this given triangle. So cosine is 4 over radical 17, and we need to square that. And sine is 1 over radical 17, and we need to square that. So this becomes 16/17 and 1/17. So the cosine of our double angle is going to be 15/17 if we doubled that angle. And then picking a formula for the tangent, that would have been 2 tangent theta divided by 1 minus tangent squared theta. I'm taking that off of our first page from our notes for the formulas that were given. So 2 and tangent is opposite to adjacent, so that would be 1/4. 2 times 1/4 in the numerator. And then 1 minus the tangent squared. So our numerator has 1/2. And our denominator, I'm going to convert that to a 16th. So we have 16/16 minus 1/16, which becomes 1/2 divided by 15/16 and 15/16. That product would be 1/2 times 16/15 for this division, which turns out to be 8/15. So using the double angle formulas graphically or from a geometric point with the triangle that was given. Now on to practice with the half angle identities. And this one we need to actually figure out what u is, since we are given that half of u is 165, then u would be 2 times 165, or 330 degrees. So we have to consider that. And the formula for the sine of half of an angle is the square root of 1 minus the cosine of u divided by 2. And the formula had a plus or a minus. So I want to consider where sine of 330 is on our unit circle. 330 is going to be over here. And sine is negative down here, but 165 is up here. And that half angle in quadrant 2, sine is positive. So we want to consider the positive angle, because we're looking at the half angle. So we've got the positive square root, not the u angle, but the half angle in this case. Now, I'm going to rewrite my formula. I prefer it a different way than what it's given on our notes. I would prefer it to be 1/2 here. I'm just pulling the denominator off, and 1 minus cosine of 330. Okay, and what is the cosine? So I got to go back to my unit circle. What's the cosine of 330 down here? Well, cosine means we're going to go square root of 3 over 2, and down 1/2 is the ordered pair at 330 degrees. So cosine is radical 3 over 2. So we want the square root of 1/2 of 1 minus root 3 over 2. Now, that could be considered, I'm going to take the 1/2 out and make this 1/4. And if I change this to a 2 over 2, so we have that common denominator to pull that 1/2 out with the 1/2 and multiply those together, we're going to have the numerator 2 minus root 3. 2 minus root 3 under the radical. And then we can use properties for square roots and take the square root of 1/4, which is 1/2, and bring that outside and end up with 2 minus the square root of 3 under the radical for our half angle identity, or the exact value for the sine of 165 degrees. This is the exact value. So here's another one. We're going to try cosine, and cosine in quadrant 2, remember we're thinking about 165 degrees. So cosine in quadrant 2, cosine is negative. It's less than 0. That means we're going to use the formula for the negative answer. And again, I'm going to rewrite my formula with the 1/2 instead of writing it as a fraction. And that formula had plus in the numerator, plus the cosine of 330. So in example A, we know that the cosine is square root of 3 over 2. And again, I'm going to write the common denominator as 2 over 2. Factor out the 1/2, put it with the 1/4. 1/2 times 1/2, and then get rid of that fraction. Take the square root of 1/4 and simplify that answer to be 2 plus the square root of 3 under the radical times negative 1/2, because cosine in quadrant 2 is negative, so we needed the negative value. And then part C, we're going to do the tangent of a half angle, and there are 3 formulas. I'm taking the second formula. It seems easy to me. 1 minus the cosine of our angle U, which was 330 degrees, divided by the sine of our angle, which is 330 degrees. So the tangent of 165 degrees can be found with this formula. And cosine of 330 we already established was root 3 over 2. Sine of 330 was negative 1/2, because in quadrant 4, cosine is positive and sine is negative in that quadrant. And getting a common denominator here, we would have 2 minus root 3 divided by 2, and that entire fraction divided by 2. So if you multiply by the reciprocal, these are going to go away, and our final answer is going to look like negative, because this is negative, times 2 minus radical 3 for our exact answer of the tangent for 165 degrees. And then example 5, we're going to look at the category for power reducing. So we want to be able to rewrite cosine to the 4th and reduce that down. So this formula, if you look back at your original notes, that's 1 plus cosine 2 theta divided by 2 is another name for cosine squared, right? So this part, cosine squared, is this formula. And we have that squared. So if you think about rewriting that, 1 plus cosine 2 theta over 2 times 1 plus cosine 2 theta over 2, you could pull out the 2's in the denominators and have that become 1/4 times 1 plus cosine 2 theta times itself. So I want to distribute 1 times 1 is 1, 1 times cosine 2 theta, and cosine 2 theta times 1 is 2 cosine 2 theta, and then cosine 2 theta times cosine 2 theta is cosine squared of 2 theta. So we just multiplied by distributive property, or FOILed those two things out. So now I see this formula again. See that? Cosine squared of 2 theta. So we're going to say this is 1/4 times 1 plus 2 cosine 2 theta. But this, let's see, let me give a red pen here. Let's say if we let u become 2 theta, then 2u is 2 times 2 theta in that case. So this becomes 1 plus cosine of 2u divided by 2, based on that substitution right here. Now we have 1/4 times 1 plus 2 cosine 2 theta, and then we're going to go back to that formula up here, 1/2 times 1 plus cosine, and if this is 2u, then that's 2 times 2, that's 4 theta. So we flipped it back to our 4 theta from here. And I can pull this 1/2 out and make that 1/8 if I multiply each one of these terms by 2. So I'd have to have a 2 times that and a 2 times that and a 2 times that to get 1/8 in the front, and 2 plus 4 cosine 2 theta, and then this would be out there, and then 1, and then cosine 4 theta. So we've taken all the fractions out to the front, and cleaning that up by collecting like terms, it looks like 1/8 times 3 plus 4 cosine 2 theta plus cosine 4 theta. So I'm with you. I'm not so sure that this seems any simpler, but what we've done is we've reduced down the cosine to the 4th of some angle. We've reduced that 4th power down to all cosine of an angle, a single power. So it makes it a little simpler. If you had to put 30 degrees in there, you could actually get a value for the cosine of 30 degrees to the 4th power. That's hurts your brain, doesn't it? And then our last example, oh no, we got 3 more examples. So example 6, we're going to solve for a double angle. Now, here's what happens. Since cosine, let's think about solving cosine for the single angle. Cosine of x is 1/2. Where does that happen? And if you like to think about the unit circle, You know cosine's positive in quadrant 1 and in quadrant 4. So cosine is a half at pi over 3 and at 5 pi over 3. So we know that for cosine of a single angle, we would have two answers, pi over 3 and 5 pi over 3. But what happens now with this double angle is that my domain changes. And how does that domain change? Because we've got the domain for 0 to 2 pi if it's a single angle. But when we have a double angle in here, you got to think about doubling that and doubling that to get that double angle, right? So if I double that angle, my domain is going to change from 0 to 4 pi. So when we think about solving this problem for a double angle, it's going to be a half when the double angle is pi over 3, or the double angle is 5 pi over 3. Now we got to go around again because our angle is stretched out. So 4 pi, it would also go 7 pi over 3 and 11 pi over 3. Whoop, I missed the 11, because I'm adding one more trip around. So 2 pi added to this would be 7 pi, and 2 pi added to this would be 11 pi. Now, this is for the double angle, and we want to solve it for x. We want to know where x is. So dividing each one of these terms by 2, because we want to solve for 1x, pi over 3 divided by 2 is pi over 6, and 5 pi over 3 divided by 2 is 5 pi over 6, and this one divided by 2 is 7 pi over 6, and this one divided by 2 is 11 pi over 6. So now we've reduced it back down to that single angle from 0 to 2 pi. So all of the places where cosine of the double angle would be 1/2 would occur at those 4 points. And I'm not going to do it here, but you might want to stop the video and check the graph for cosine 2x on your calculator and 1/2 on your calculator, and graph those two and notice that it crosses in 4 locations. So example 7, you could try this one on your own and then turn the video back on to see if you come up with the same answers I do. So again, like example 6, what I'm thinking is I want to know where the sine of 2x is 0, and I've got to adjust my domain by multiplying everything by 2. So my domain is going to go up to 4 pi, and 2x is 0 at 0, at pi, at 2 pi, and at 3 pi. So solving for x, I'm going to get 0, pi over 2, pi, and 3 pi over 2. And again, you can check that with your calculator. On our last example, okay, so this can be a little challenging. I've used the cosine 2u as 2 cosine squared u minus 1 off of our first page of notes. And that way I can replace cosine 2x with this formula here, or this identity. So that'll give us everything in terms of cosine. So we could say 2 cosine squared x minus 1 plus cosine of x equals 0. And if I move the 1 around, you can see you've got a binomial, a trinomial here that can be factored as the product of 2 binomials. 2 cosine x minus 1 times cosine x plus 1. And our goal here is to find all the places where this graph is 0. So the zero product property says when two factors are multiplied together and the answer is 0, then one of the factors has to be 0. So this first factor, 2 cosine x minus 1, that first factor is 0 when cosine is 1/2. And cosine is 1/2 when x is pi over 3 and 5 pi over 3. The other factor, cosine of x plus 1, is 0 when cosine is -1. And that happens when x is pi. So we have 3 times around the unit circle when the graph first is 0. But we, like I said, we wanted to be the general solutions. So in general, we can rewrite these 3 answers and develop a pattern. So the first one, pi over 3 plus every 2 pi radians. Or the second one, 5 pi over 3 plus every 2 pi radians. And then the third one at pi plus every 2 pi radians, where n is an integer. So you see we have 1/3, 3/3, 5/3, and then if you keep going where n is an integer, so say -3 or -2 or -1 or 0, 1, 2, so on. So if I put 0 in here, I got pi over 3. If I put a 1 in here, I've got 7 pi over 3. If I put a 2 in there, that's 13 pi over 3. And you can see how it would develop 1/3, 3/3, 5/3, 7/3, 9/3. So we've got a pattern that's odd multiples of pi over 3. Okay, so those odd multiples of pi over 3 can be written using the pattern 2n minus 1, where n is an integer, where n belongs to the integers, times pi over 3, and that would develop every single time that our graph has an x-intercept. So this is called a general solution. And we'll see more about that in the last lesson, but next time we'll look at some application problems using law of sines and then law of cosines. See you next time.